Hello again, everyone. This is Nicholas speaking. Welcome back to the FE Review Workshop Mechanical section. Good to talk to you all again. Today we are going to be going over some power cycles and entropy problems for the review of the FE exam. We're going to be going over, looks like 4 problems today. Hopefully we touch everything that we need to. Alright, so again, without further ado, let us get into some of these problems. If you are looking at the handout, I should say the email out, we are going to be starting with problem number 2, which talks about compression in a standard Otto cycle. So a lot of you, if you've taken this class at Cal State Long Beach, particularly with Mr. Dr. Hashenpour, you may be familiar with drawing out all of these different cycles, regardless of what they are and what kind of problem you're looking at. Though for many of these, you're actually not required at all to draw out the cycle, and doing so might confuse you more, or it might take up more time than you need. So very few of these problems actually require you to draw out the cycle, at least in the particular edition of the problems that we're looking at. For maybe the higher caliber ones, which are not contained in this book, might need you to draw one out if, say, you needed to find some of the temperatures or whatnot. But we're looking more at some of the general problems that you can get asked from anywhere from the easy to intermediate level. So let's get into this. We have at the start of our compression in a standard air standard Otto cycle with compression ratio, or we're going to call compression ratio RC, of 10. And air is at pressure 1. Air is at 100 kilopascal and 40 degrees Celsius at the start. Okay, P1, 100 kPa and 40 degrees C. We have a heat addition, Q in. It's going to be 2,800 kilojoules per kilogram. We want to know what is the thermal efficiency. Alright, so we're actually given quite a bit of information here. Now, what information in here is actually useful? Since we're asked for the efficiency, we know this is again something that you can look up in your little handbook, or whatever the book, handbook in for the exam in the equations section. Man, I'm gonna butcher this Greek letter. Eta is equal to 1 minus RC to the 1 minus K. This is pretty much all we need to solve this problem. The second and third pieces of it, or actually all of this information that we were given here, does not really matter at all. It is shown there to throw you off and make you think there's a longer problem than it actually is. So we have our RC, that's 10, and then our K for air is 1.4. So how do we put this in the equation? It's gonna look like 1 minus 10 to the negative 0.4. This will give us an answer close to 0.602, which corresponds to the 60% efficiency, being answer choice B. So this problem basically gives us a lot of unnecessary information that we do not need. And instead you can get the solution very simply with just the efficiency equation. There's actually another one of these that is much longer that you can use if you are using a diesel cycle. Again, most likely will be in the handbook as well, so you can use it there. Okay, the next problem we're going to be looking at is going to be a Carnot Refrigerator. So if you guys remember what Carnot means, is pretty cool. It means you get to assume a lot of efficient stuff. So we have a Carnot refrigerator receives heat from a cold reservoir. So we have our cold reservoir. Let me, let's go blue. We have our cold reservoir here. And this is going to be at a temperature 0 degrees Celsius. The power input, W dot 1750 watts per ton of refrigerant. What is most nearly the coefficient of performance? Oh my, they are asking for the coefficient of performance now. This is another dimensionless number that you can get various ways, though it's also fairly simple to calculate. It doesn't require a lot of complicated math. There's a couple of different equations for it. There's the one relating your TLs and your THs. There's COP TL over TH minus TL. There's also another one, which is QL over work input. Which is the rate of the heat transfer to the power input. Oh man, I think I wrote this wrong. It says receives heat from a cold reservoir. It's not a temperature. I mean, it is a temperature, but it's receiving QL from this reservoir that's at 0 degrees C. Yeah, okay. And then we're going to power input. So what we can do with this is we can find our coefficient of performance using our power input, W. We have units Celsius as temperature and watts per ton of refrigerant, so we're gonna have to do some conversions here really quick. We have 3516 watts per ton per 1 ton divided by 1750 watts. The 3156 is converting to the other system, to the SI system, or converting from the tons of refrigerant to the watts, specifically just watts, because we need just watts in order to do this calculation. All right, so with this, if we work out this, in the end we get these will cancel and also these will cancel, which will give us 3516 over 1750, the dimensionless unit, which is the correct units for coefficient of performance. That'll be about 2.01 or 2.0 as our answer, which will leave our choice with D. So this problem has a more specific version of the COP formula and requires you to do some unit conversion, but other than that, everything turns out to be okay in the end with a nice simple calculation. Okay, let's look at problem number 6, which is kind of similar to this one in asking for a coefficient of performance with a slightly different situation. This one might be a little more memorable to some of you. This was problem number 3, by the way. All right, problem number 6. A Carnot refrigerator operates between two temperatures, -11, I'm going to call that the low temperature, and then our high temperature, 22 degrees C. What is the coefficient of performance? Okay, so remember back to that equation that I wrote down for the previous problem. TL over TH minus TL. Do you know that this only works for a Carnot Cycle refrigerator? Since you can assume the temperatures, you can assume the efficiency to be perfect, and these temperatures also being right at that, you can have the temperature differential be its maximum. Otherwise, there will be a small deviation in that, which would affect the coefficient of performance. Okay, what is our TL? We're going to convert everything to Kelvin to make this work out. Over 22 plus 273 minus -11 plus 273. What do we get as a result of this? A coefficient of performance of around 7.9. Now, where does that put us? Answer choice D. Do note it's not necessary to change the temperature to Kelvin, though it is a good habit to have, since some of these problems will require you to work in Kelvin, and knowing how to do that is a benefit. Okay, then let us move to our last problem here, number 7. Problem number 7 is another Otto cycle. What are the processes in an ideal Otto combustion cycle? Otto combustion. So with this ideal Otto combustion cycle, how are we going to be able to break this down so we can analyze it? This is one of those problems where you may find benefit in drawing out the cycle itself with the PV or the TS diagram. For this one, it will be helpful to draw out the PV and or TS, depending on which one you like. This one you can use both, but I'm going to draw the TS, because that one will be useful in determining how this cycle will work. Allow me if I could just draw straight. Okay. Okay, so we have point A here. Point B here. We will go up here to C, down to D, and back over to A. That should be a slightly curved line. All right. So with this, you can see what's going on in this picture. We have S is our entropy, T temperature. We can see we have two sections on this. We have A to B, we have AB and CD, which are isentropic. All right, and then we can see that the temperature between, or sorry, that the temperature and entropy are changing from B to C and D to A. So B to C and D to A, or we know that there's going to be heat addition or heat loss, because we know the temperature and entropy are changing. Now, this is a good time to look at the other diagram, since we don't really know what this means based just on the TS diagram here. So let's go look at the other diagram, PV. PV diagram will start A here, we'll go up to B, then to C, then to D, back to A. Sorry for the messy writing. So here, we can see that there are two sections where there are, should be a straight line, where there are constant volume, that being BC and AD, or DA. Constant volume. Also being where we have our input of heat. If this were a piston cylinder, the compression cycle would occur here. So this would be work in. Heat in will be the explosion of the gas fuel mixture in the chamber. That's our Q in after our work is in. Then our work out would be the expansion as the piston retreats. And then here being the Q out, the heat rejection. Though that stuff is not really necessary for this particular problem, it's cool stuff to know regardless. So now what do we have? Our answer choices have a bunch of different, it basically is saying we have two constant volume processes, two isentropic processes, two constant pressure, two isentropic. It doesn't specifically say these A, B, C, D, B, C, D, A. So all we know is that there are two processes that are isentropic and two that are constant volume. Does this reflect any of the answer choices here? Two constant pressure is not correct. A has two constant volume and two constant, or I should say isentropic. Well, I mean, which is actually just our answer straight up. That is the correct answer. B was stating two constant pressure and two isentropic. The latter is correct, though there are no constant pressure processes in an Otto cycle. There is one in a diesel and two in a Brayton, but we're not dealing with those. Two constant volume processes and two constant temperature processes. Again, there are no constant temperature processes in this particular system. And then D is two constant pressure processes and two constant temperature processes. Both of those are completely incorrect for an Otto cycle. So that leaves us again with A as our answer. All right then. I thank you all again for joining me for this little exploration into some of these FE problems. I wish you all the best in the current situation, and please let me or any of the other tutors know in the comment section below if you have any questions, problems, if you like the video or not. And I will see you again next week. Take care.